Hello, I'm Carla Moldaven. In previous sessions, we've looked at mathematical modeling a little bit. We did an experiment with density and with a bouncing ball and a viewing tube and melting ice. And today I've got another simple experiment that we're going to set up and look at the data with it. This one's the hinged mirror experiment. You may need to borrow my hinged mirrors to do this one. These are available from some places that sell math manipulatives. This is a simple mirror that's hinged, and I've got a protractor that I can put the center point there at the vertex of the angle here where those two mirrors come together, and I would be putting the zero line straight through the middle of this mirror, and I can read the other angle size off this other side of the protractor. For right now, I'm going to just take a mirror that's straight out like that. So that means the angle between these two halves of the mirror would be 180 degrees. And what we're going to do for our independent variable is to vary the number of degrees that this is between these two halves of the mirror. And we're going to look directly into the mirror, open at those different angle sizes, and count the number of images that we can see. And with the images, I'm including the original object itself. I've just used a little mineral specimen. You could use a pattern block or a colored chip or anything like that to be the thing that you're looking at. So if I went back to my 180 degree angle here, a straight angle, I would be able to see my original specimen here and one reflection. What if I changed it to 120 degrees? So I've got this one going through 0, this one's going to go through 120, and if I look straight on through that, I'll be able to see 3 images, 2 images plus the original object. If I adjust it to 90 degrees, then I'll be able to see 4 images, the original plus 3 others. Now, you may not be able to see them very well using the camera on this, but I've already collected the data for us. So if we look at the data that I've collected, these are the angle sizes and the number of images that can be seen. With the 180 degrees, we could see the 2 images. With 90, we could see 4. If I adjusted it to 60, I would be able to see 6. With 45, I'd be able to see 8. With 120, I'd be able to see 3, and with 72, I'd be able to see 5. So I've got these in different orders here. I might have preferred to list them in numerical order, but the question that you might think of first, since you've done with so much with linear equations, is this a linear relationship? What would it look like if it were linear? It would mean that the same change in an x value would result in the same change in a y value. In this case, we went from 2 to 4 images. On the y value, that was an increase of 2. And when we went from 4 to 6, that was 2. Well, if this were linear, the decrease here from 180 to 90 ought to have been the same decrease as from 90 to 60, but it wasn't. So this is definitely not a linear relationship. So then I might want to ask, well, what kind of relationship is it? Is it quadratic? Is it exponential? What kind of function do I have on my hands here? And the relationship sometimes is harder for students to see. They look for something complicated, and then when you give them a hint, then they get where they can see it a lot more easily. Notice that this is true. If I multiply the 180 times 2, I get 360. If I multiply 90 times 4, I get 360. 60 times 6 is 360. 45 times 8 is 360. 120 times 3 is 360. And 72 times 5 is 360. So what we have is that our angle size, which we'll call x, and our number of images, which we're calling y, x times y is always equal to 360 degrees. What would be another form we could put that equation in? What if we solved it for y? We would need to divide each side by x, so we would come up with 360 divided by x. I could call that a rational function since I've got an algebraic fraction with a variable in the denominator. This one is also an example of an indirect proportion. Or I've got two variables that vary inversely. As one increases, the other decreases, and it's a multiplicative relationship. So that means if I used this equation we've come up with, if I let my angle size be 10 degrees, then my number of images I should be able to see would be 360 divided by 10, which would be 36 degrees. Now, if you try that with the mirrors, you will have a hard time distinguishing the 10 images, but that would be the relationship there. We could also call the 360 the constant of proportionality. And usually if you looked at the equation for an inverse proportion, you might see it as y is equal to k over x, where k is your constant of proportionality. So how was it that we saw that we would have an indirect proportion or an inverse variation problem? What we saw in the pattern is that the two variables, x and y, are always multiplying together to give us the same constant. So you could have had x times y is equal to some constant, which is the same thing dividing by y by x as having y is equal to k over x. So that was the way we recognized the pattern for this inverse proportion, that the x and y values always multiplied to give 360. And could we explain geometrically why that makes sense? I like to think of it in terms of having a circle and having, let's say, a hexagon inscribed in that circle. So if I had this hexagon inscribed in this circle, each of these triangles would be an equilateral triangle. So each of these would be 60 degrees. And if I had an object in here, and this were the mirror right here, the hinged mirror, I would be seeing an image in each one of those congruent triangles that make up that hexagon. So it's interesting to see the connection between the geometry and the algebraic relationship between the numbers. And our relationship, we said, could be modeled with the equation y is equal to 360 divided by x. And we probably could have come up with that without doing the experiment. But doing the experiment gave it a different kind of flavor as far as having to collect the data for ourselves and not necessarily seeing up front why that would be true geometrically, but analyzing it algebraically and numerically first. So this one's an example of a rational function, or it's also an example of an inverse proportion. So in that short experiment, it gave us a chance to model a function that would not be linear, since we've done so much with linear. And as I've mentioned before, we can do some other types of modeling. You can look forward to exponential and logistic and other kinds of models. These will help you in your interpretation of relationships between variables and things that we encounter in our daily lives. Thank you.